If you want to squeeze the most accuracy out of your precision hand loads, finding the proper seating depth is critical to the load development process. Lately, I've been doing some testing on the process put forth by Eric Cortina in his Chasing the Lands is Stupid video, and I have some very interesting results to share with you today. Implementing this testing process may just be the most effective way to shrink your group size with the least amount of testing, but you're going to need to stick around to find out. In today's video, I'm going to quickly review how this process works and show you exactly what I did and the results that I was able to achieve. I don't want to rehash Eric's whole video for you, but in short, he discusses how to find the accuracy node and make sure you stay in that node. It's certainly a good watch, and I encourage you to watch it if you haven't yet. What some people seem to struggle with in this process is that Eric does not discuss this tuning process in relation to the lands or how far the projectile is jumping. He doesn't care. All too often, and I am guilty of this as well, reloaders talk about cartridge overall length in terms of jump and how far the lands are away from the projectile. One of his major points in the video, as I understand it, is that as your barrel wears in, you do not want to keep changing your cartridge overall length as your lands erode. That is, unless your groups show you that you need to. This involves not monitoring your lands dimensions as your barrel wears, but shooting groups to find out when it's time to change your cartridge overall length. Would you put chains on your tires if there isn't any snow outside, just because the thermometer says that it's cold? Likely not. You only want to change this dimension because the results on the paper tell you to. After all, group size is what we care about, not the distance the projectile actually jumps. Thinking about this another way, we have all probably heard the term, the definition of insanity is doing the same thing and expecting a different result. Why is it then we expect to change the input, the cartridge overall length, and expect the same result, good groups, at the other end? If you'd like to learn more after finishing watching today's video, I'm going to link to a playlist at the end where you're going to be able to catch all the videos I've done on this subject, as well as Eric's videos on this subject. Today's video is all about running through the process and testing our result. When starting this test, you need to have a couple things figured out, or at least a real good idea before you start. The first thing is your neck tension, as this will affect the jam dimension. The second thing you need to know is your powder charge. The neck tension that I'm using for today's test, I'm just going to call 2000s. But in actuality, the neck tension is the result of annealing every single case, full-length sizing without the expander installed, and then using a 21st century expander mandrel 2/1000ths under projectile diameter, so 0.262, to set the final neck dimension. I have a whole video on finding jam, as does Eric, and they'll be listed in the playlist as well. The second thing you need to have figured out is your powder charge. I'm not sure how exact this really needs to be. Obviously, for this particular load, I've had a pretty good load worked up with it already, and so I'll be using that powder charge. But from what I've seen Eric recommend, he's doing something similar, not exactly the same as the Satterley load test. We're loading incremental charges to find a spot where the standard deviation and extreme spread is low. Once we have a good combustion figured out, having a low extreme spread, then we're going to run the cartridge overall length test to tune that to see how it works. Our test platform is a Ruger precision rifle, chambered in 6.5 Creedmoor, and installed on it, it has a 26-inch white oak precision barrel. Today's test will be using the 140 grain ELDM by Hornady. I have had what I consider to be great success with this projectile in almost every application that I've used it in, and that's the reason why I picked it for today's test. When I ran the jam test, the dimensions that I have are going to be in the table on your screen. Admittedly, this might be slightly confusing because the expander mandrel we use to size our brass is not listed in our table. However, with that neck tension value, I had a bit of trouble getting a reliable reading. And that's what I talk about in my video, Finding Jam. The table on our screen has all the information we need to know, and we did have reliable results with the 263 expander, and so those are the dimensions that we're going to be using. So jam for our application is going to be a cartridge-based to ogive measurement of 2.270 inches, and a cartridge overall length measurement of 2.8905 inches. When starting this testing, Eric recommends starting at jam minus 20,000ths, and seeing the projectiles deeper in 3,000ths increments. If this seems complicated at all, you can simply pick a value that you know the projectile isn't even contacting the lands and use that number as a starting point. He does talk about using 3-shot groups at least to start with. This will keep your needed round count slightly lower. However, I will agree, you may not know how good a group is with 3 rounds, but you can certainly determine that if it's bad. At least, I've never seen a group get smaller the more rounds that were fired. That aside, we're going to go back and verify this after we've determined our optimal value, which is what we're primarily doing in today's video. Our baseline load that we're hoping to improve on is one I've been using for quite a while here on the channel. We're using, again, the 140 grain ELDM, part number 26331. We're using 41.3 grains of Hodgkin H4350. My baseline load has a cartridge overall length of 2.858 inches with a CBTO measurement of about 2.233 inches. I've actually tested this load with several types of brass, large rifle primers, and small rifle primers. For the large rifle primers, I seem to prefer the CCI 250s, and small rifle primer brass, I've been using the CCI 41. The baseline groups for how we're starting today are pretty typical for how this load has been performing in our rifle. Typically right around a half MOA. In fact, the last two test groups that I put on paper with this particular load measured one 5-shot group at 0.565 MOA and another at 0.539 MOA. So essentially just over half MOA. And that's pretty repeatable. Depending on the person or application, you may be ecstatic with that or completely disappointed. But for today's test, you can decide what you think. That's the baseline we're going to go with and that we're hoping to improve. We actually talked about this first stage of testing in a previous video, but I want to make sure everybody's on the same page. Now in Eric's video, he describes accuracy nodes and sine waves. So essentially, as you change the cartridge overall length, groups will get bigger and smaller, and that is why I graphed it in this fashion. The graph I'm showing you on your screen, I have showed this graph before, but we're going to have new data today. I promise we're getting there. But we tested 16 groups. We started with the JAM CBTO measurement of 2.270 inches, subtracted 20 thousandths, and so our first measurement for our graph is starting off at a CBTO of 2.250 inches, and we will be moving further away from JAM in 3,000 steps. We could go over all these groups again. I did show all of these in the last video on this particular subject. However, we're just going to talk about them as they're plotted on the graph. We can see how the graph varies. We started off our first point. We had a 3-shot group of 0.342 MOA, and as we graph all of our groups, what we're really looking for is a large sequence of small groups. We don't want to pick one cartridge overall length to test that's surrounded by groups that are not the size that we're looking for. For example, our group at 2.238 inches, even though it was a 0.253 MOA group, having larger groups on both sides of that, it's not something we want to pick. Moving a little further down the line, we can see the largest sequence of smallest groups was actually from a CBTO of 2.232 inches to 2.226 inches. And in fact, on our graph, we can see that our standard load, which had a CBTO of 2.233 inches, would have performed somewhere between a 0.384 inch group and a 0.658 inch 3-shot group. So it may not be a huge surprise that our baseline load performed at just over half MOA. Eric's advice, if I understood it correctly, was to pick the largest value, which would have been the CBTO of 2.232 inches. But since the group that we had at 2.229 inches was just a little bit smaller, I wanted to move slightly shorter to that. So for today's test, we're going to validate the CBTO of 2.231 inches. Also, because I can't stop tinkering, if you're looking at our chart, you can see at the CBTO of 2.205 inches, it actually had a 4-shot group at 0.268 MOA. I couldn't possibly resist not exploring that area a little bit further, so we're going to gather some more information, some more data around that node today. Essentially, we want to know if that's just one spot or if multiple small groups are going to be attained around that cartridge overall length. So our load data for today, we're actually using twice previously fired liable brass. It's been annealed, full-length size. We're using our 21st century 0.262 inch expander mandrel. The projectile is the one we've been talking about, the Hornady, part number 26331. The primer we're using is the CCI 41. Our powder is Hodgkin H4350 with our same 41.3 grain charge. And what we're actually testing today is various cartridge overall length, but we're going to talk about it in CBTO because that's a more reliable measurement. So the first groups we're going to test, we're going to be talking about at a CBTO of 2.231 inches, but we're also going to repeat our CBTO test at 2.205 inches, 2.202 inches, and 2.199 inches to make sure that if we were to load in that node, we would have adequate sample size and we would know how wide that node is. For our first test, we're using our magnetospeed to get our velocity data. 5 rounds, all sliders loaded at exactly the 2.231 inch load. Our first 5 shots averaged 2775 feet per second. The standard deviation was 6.4 and our extreme spread was 16. After that data was generated, we removed the magnetospeed and shot for groups. So I'm not going to be giving you any velocity data on the rest of our groups today. At our CBTO of 2.231 inches, our first 5-shot group yielded a 0.385 MOA group, and our second sample was at 0.413 MOA. Overall, a measurable improvement of about 1/8 of an MOA. Is this the best cartridge overall length? Maybe not. But these are the best 5-shot groups that I've had out of this load. Now, let's look at the additional data we generated as well. Keeping in mind our previous test at a cartridge-based ogive of 2.205 inches, we had that 4-shot group of 0.268 MOA. We're going to repeat that same load today. Our 3-shot group had a very respectable 0.304 MOA group. So again, a repeatable small group. Shrinking our cartridge-based ogive to 2.202 inches. We had another good size group at 0.288 MOA. And our group at a CBTO of 2.199 inches, we had a 0.275 MOA group. If we update our chart, we can see that our biggest and best consecutive area for 3-shot groups anyway that we had is now down around our CBTO of 2.205 inches. So despite being able to shave off 1/8 of an MOA, at least what I've been used to already, it looks like we may be able to shrink our groups even further by testing a CBTO down at 2.204 or 2.203 inches. This will put us well out of our rifling altogether and makes our cartridge overall length in that area somewhere around 2.824 inches. Easily ran in any of our magazines, whereas our other load, having a cartridge overall length of 2.851 inches, will not fit in the stock PMags. Overall, in my opinion, I think that this test was successful in improving our groups. I'm afraid I can't ignore the groups down at that shorter end either though, and I'll need to repeat a larger sample group at those cartridge overall lengths to see if they look as good with larger sample sizes. I'm interested in your feedback below. What do you think of this process? If you've tried it, what were your results, good or bad? When we picked our sample size to demonstrate this process, we talked about a projectile that has worked pretty well for us in the past. Would you guys be interested if we used this process to tune a load, which we really haven't had great success with, to see how it would perform? Or what do you think would be a better way of validating the validity of this testing process? I'm always interested to hear from you guys in the comment section below. If you'd like to see more data on how this process works, basically this entire series from start to finish, I'm going to post a playlist here so you can check that out. It's going to walk you through all the steps that you'll need to know. Like, subscribe, and all that fun YouTube stuff. I hope to see you come back next week. And until then, stay safe in small groups.